In the previous two lectures, we completed cascaded systems, and now I will explain working of Darlington pair. Darlington pair or Darlington transistor is a compound structure. Darlington pair is a compound structure. We are calling it compound structure because it is having two BJTs. Darlington pair is having two bipolar junction transistors, and these two BJTs are connected to provide a very large current gain. Very large current gain. So we use Darlington pair in the applications which require very large current gain. You can see the construction of Darlington pair. The connection is made in such a way that the current amplified by the first transistor is further amplified by the second one. This transistor is the first transistor, let's call it Q1, and this transistor here is the second transistor, let's call it Q2. The current, the input current IB1 is amplified by Q1, and the output current is IE1. This output current is further amplified by the second transistor Q2, and the output current of the second transistor is IE2. So the input current is IB1 for the Darlington pair, and the output current is IE2, and there is double amplification, and because of this reason we also call this transistor super beta transistor. Let me write this down. We also call it super beta transistor, and these two transistors works as a single transistor. You can see this terminal is the base terminal, this terminal is the collector terminal, and this terminal here is the emitter terminal. So we can consider these two transistors as a single transistor, and let's call this single transistor Darlington transistor QD. The current gain of the Darlington transistor is, let's say, beta subscript D. Current gain of the first transistor is beta 1, and current gain of this second transistor is beta 2. Now we have to find out beta D. Beta D is equal to beta 1 multiplied with beta 2, the current gains of these two transistors. We will prove this shortly. Darlington pair was invented at Bell Labs. It was invented at Bell Labs by Sidney Darlington. In 1953. Now let's prove this point. Beta D is equal to beta 1 multiplied with beta 2. You can see the input current is equal to IB1. The input current is equal to IB1, and the output current is equal to IE2, and the current gain is equal to output current divided by the input current. This means the current gain is equal to IE2 divided by IB1, and we already know the ammeter current is equal to sum of collector current and the base current. The collector current is equal to beta times IB. The collector current is equal to beta times IB, and we are talking about general case. So IE is equal to beta plus 1 IB. Beta is a large quantity, so beta plus 1 we can write as beta. So IE is equal to beta IB. And if we talk about the second transistor, IE will become IE2. Beta is equal to beta 2, and IB is equal to IB2. Now in place of IE2 we can write beta 2 IB2. So here we have beta 2 IB2 in the numerator divided by IB1. IB2 is the base current of the second transistor, and two different currents cannot flow through the same wire. This means IE1 is same as IB2. So in place of IB2, we will have IE1, we have IE1, and again using this result, we have IE1 equal to beta 1 IB1. So IE1 we can write as beta 1 IB1. We have beta 1 IB1. IB1 will cancel out, and the current gain is equal to beta 2 beta 1, and the current gain for the complete system is equal to beta D. So beta D is equal to beta 2 multiplied with beta 1. So we have proved the above point. The next point is related to occupied space. You can see we are using two transistors, and these two transistors are sharing the same collector. The collector is same to these two transistors. So if we compare the space occupied by the two individual transistors, then the space occupied by the Darlington pair is smaller. I will repeat this point again. The space occupied is lesser than two individual transistors because Darlington pair is using the same collector or shared collector. The next point is related to base emitter voltage. The base emitter voltage of the first transistor is, let's say, VBE1. The base emitter voltage of the second transistor is, let's say, equal to VBE2. Therefore, the base emitter voltage of this transistor, the Darlington pair, the overall base emitter voltage VBE is equal to VBE1 plus VBE2. And if we consider VBE1 nearly same as VBE2, then VBE is nearly equal to twice of VBE1, and this is one of the disadvantages of Darlington pair. We do not want the base emitter voltage to be high, but in this case the base emitter voltage is twice as compared to the base emitter voltage of the normal transistor. If Q1 is silicon transistor, then VBE1 is equal to 0.7 volts. If Q2 is also a silicon transistor, then VBE1 is same as VBE2 and they are equal to 0.7 volts. In this case, the base emitter voltage of the Darlington transistor is equal to 1.4 volts. And when two transistors are germanium transistors, then VBE1 is same as VBE2 and they are equal to 0.3 volts. This implies VBE is equal to 0.6 volts. Now we will discuss the case when the two transistors are not same. Let's say Q1 is a silicon transistor and Q2 is a germanium transistor. In this case, VBE1 is equal to 0.7 volts. VBE1 is equal to 0.7 volts and VBE2 is equal to 0.3 volts. This implies the barrier potential of the Darlington transistor is equal to 1 volts. So this is all for this lecture. In the next lecture, I will try to explain the practical application of Darlington pair. We will use breadboard, LED, resistor, voltage source and 2 NPN transistors. So in next presentation, we will construct a circuit on the breadboard depicting the practical application of Darlington pair. If you have any doubt in this lecture, you may ask in the comment section. I will end this lecture here. See you in the next one.